Okay, we're going to take a look at problem 14-5. And what we're going to do is we're trying to find the height h uh, relative to point B. So from A relative to point B, the difference in height between those 2 points. When the roller coaster is released, it, it reaches a velocity of 100 kilometers per hour when it gets to point B. The second part of this problem, we're going to look for this instantaneous radius of curvature at this point such that the passengers don't experience more of a normal force than 39.24 times their um, mass. Or if we want to look at it from this perspective, no more than 4g, right? Essentially. Okay. Okay. So first part of this problem, we're going to have, so we're looking for h, and we're also looking for rho b, which what I call the normal force at point B, basically, of the passengers. And I said it's got to be essentially less than or equal to this. Okay. So we're given some quantities. First thing is the velocity at point B is 100 kilometers per hour. Um, I also defined m, a mass, being just so when we go through and do the calculation, it's the car and the person put together. It really doesn't matter as long as it's either the mass of the car or the mass of the person. Since the second part, we're actually looking for the person. We'll use that as the mass. Okay. Um, and we also have an initial velocity, right? So we have velocity at point A. So we're releasing it at that point. At point A, no velocities given. So we can make the assumption that the initial velocity was zero. All right, so here's our governing equations for this problem. It's a work and energy problem. So you have some initial kinetic energy associated with the car and the passengers. And you're adding it, you have some work being done going from point one to point two. In our case, it's really TA and TB. And we have some final kinetic energy. Okay. And there's different ways to look at this problem. You could think about it in terms of like potential energy. Starting off at point A, you have potential energy, and that's going to get converted all the way over to um, kinetic energy by the time when it gets down to point B, or point two in this case. The second equation that we're going to need for this problem, we're going to need to find our instantaneous radius of curvature. We're going to use Newton's second law of motion. Okay, and in this case, we care about the force in the normal direction, right? So I'm going to write it in terms of the force in the normal direction. All right. First part of their approach, what we could do is, one of the things we recognize is this kilometers per hour. We're going to need it. We're going to be working with meters, meters per second. So we're going to convert over to meters per second. So we just perform that conversion. The second step, at least this is the approach I did, um, which is pretty close to the author's approach. We apply a work and energy equation to solve for h. Okay. And what you're going to notice is that it's really independent of mass. You can cancel out mass. This is my work, work of the weight. And here's my kinetic energy on the right side of the equation. And the mass in this case, I just wrote it as mass equals mc plus mp. It really doesn't matter, but it's the same mass. So you can cancel out the mass here, cancel out the mass here on both sides, and then just go through and solve for h. Okay. Okay. The second part of the problem is we're looking for the instantaneous radius of curvature. And what we could do is we just create like a simple free body diagram. I had it as a person, and here's the normal force of the car pushing back up on the person. And here's the force going down, the mass of the person times gravity. And here's the normal force pushing back up. Okay. So we use Newton's second law of motion equation for this. And basically, from this free body diagram, what are we going to have? Here's our force going down. Here's our normal force defined as this. So this is like our limit, right? So we're basically putting in the limit into the equation. Well, we can do it with the mass of the person. So eliminate the mass of the person on both sides of the equation. And then we can solve for the instantaneous radius of curvature. And that is pretty much it for this problem.